Everyone talks about giant models with billions of parameters, but here is a secret that makes them far less intimidating. A transformer is really just one small unit, repeated over and over and over. Understand that single unit, and you understand BERT, GPT, Llama, and virtually every large language model in existence. It takes a sequence of vectors in, and it returns a refined sequence of the very same shape, ready for the next copy of itself. So what is actually inside this humble, repeatable brick? Let's open it up and take a proper look. Inside a single block, the data flows through a fixed, elegant sequence of steps. Follow it one stage at a time. Start by normalizing the input, then running multi-head self-attention. This is where every token gathers relevant information from all the others, mixing context across the sequence so that each position sees exactly what it needs from the rest. Then add the residual. The block adds attention's original input back onto its output, so the layer only has to learn a small correction, and gradients get a clean highway straight through the network. This residual wrap around the attention sublayer is a big part of why very deep transformers train at all. Next, normalize again and run the feed-forward network. Applied to each token independently, it expands a vector out to a much wider hidden layer, applies a nonlinearity, and projects it back down. This is where most of the heavy per-token processing happens. Finally, add the residual once more and pass the sequence onward. The output carries the exact same shape as the input, which is precisely why you can stack this identical block again and again into a deep tower. Step back for a second. Why does this one seemingly boring block matter so enormously? You might expect every task to demand its own bespoke architecture, hand-designed for translation, or classification, or code generation. That is how a lot of machine learning used to work, and it meant reinventing the wheel constantly with fragile, hyper-specialized designs that rarely transferred. Instead, a single uniform block does it all. Stack the very same unit, scale up its width, its depth, and its training data, and you get BERT, GPT, Llama, and essentially every modern language model. The real magic is repetition, not some exotic secret component. It is a genuinely humble idea, and that humility is exactly what made it so easy to scale. Boil it all down, and three ideas define the transformer block. It is attention plus a feed-forward network, wrapped in residuals and normalization. Self-attention mixes information between tokens. The feed-forward network transforms each token on its own, and residual connections with layer normalization keep the whole thing trainable and stable. It takes a sequence in and returns the very same shape out. Because the output dimensions exactly match the input, blocks compose cleanly. That fixed interface is what lets you chain a dozen of them, or well over 100, into one deep stack. Stack and scale it to build every modern language model. The same brick, repeated and widened, gives you tiny models and frontier models alike. Decoder blocks use causal attention, and whether normalization goes before or after each sublayer is a key stability choice. All right, let's lock in what matters. A transformer block is the single repeatable unit that, stacked dozens of times, makes up an entire transformer. Each block wraps two sublayers, multi-head self-attention, and a per-token feed-forward network, with residual connections and layer normalization around both. It takes a sequence of token vectors and returns a refined sequence of the exact same shape, which is what lets the block stack seamlessly, one after another, in a tower's dozens or even hundreds of layers deep. Scale that humble unit up in width, depth, and data, and the very same structure becomes BERT, GPT, and Llama. If seeing the building blocks this clearly appeals to you, we take apart many more over at Standarity.com. Come put the pieces together with us.